Alright, this is video 4 for Math 2210. We have two questions we're going to cover in this video. The first question is to find the equation of the tangent plane and the equation of a normal line to the surface at a given point, which the point that we're told is at the point 222, for the level curve of f of x, y, z equal to 12, where f of x, y, z is equal to 4x squared minus 2y squared plus z squared. So let's just first write down the level curve, or the thing that we're interested in here. So we'll focus on the tangent plane. So we must find the tangent plane to this guy. It's really 12 equal 4x squared minus 2y squared plus z squared at x, y, z equal 222. So this is the question that they're asking us with this level curve setup that they've got here. And the way to do this is to take the right hand side of this equation right here and to call this another function, right? So we call this guy, or maybe we can even just use this function up here, right? This has already been named that, and we need to find delta f of x, y, z, right? We need to take the gradient of this guy with respect to those three variables. So when we do it with respect to x, we get 8x, y would be minus 4y, and then 2z. And we need to evaluate this at the point 222. Right? And if I do that, I get 16 minus 8 and 4. Okay. So we've done something. We found the gradient at the given point. And we know that a plane is defined by a vector pointing normal to it, right? If we give you a point and a vector that points normal to the plane that we're interested in, those two things will define a plane. And so we know that the tangent plane, right, the gradient is always normal to the tangent plane. That's how it's set up, right? The gradient is normal to the surface. So all I need to do here now is just use these coefficients in the equation of the plane, and I will get the equation of the tangent plane. So that is going to, so our tangent plane is the following then. It's going to be 16 x minus, the point that we're interested in here was 2, so 2 minus 8 y minus 2 plus 4 z minus 2. So the minus 2's are coming from the point that we're interested in. This is like my, let me use another color here. This is like x naught, y naught, and z naught. And then these guys are the partials, right? These guys right here are coming from the partials with respect to each of the variables x, y, and z at the given point, right? So this is like my f of x evaluated at 2, 2, 2. F of y at 2, 2, 2. And f of z at the point 2, 2, 2. Okay? And that should be kind of familiar. You should, I think there's a equation just like this in your textbook where it shows you how to set up this equation of a tangent plane. So now we can, if we want, simplify this up, multiply things around, and I'll just do that quickly. I think we would get what? 16x minus 8y plus 4z minus, let's see, this is going to be minus 32 plus 16 minus 8. I think that's what, plus 24? Or minus 24, excuse me. Right, equal to 0. 16x minus 8y, so this now gets simplified. This is, organize my work here, equal to 24. And I may as well just divide off of 4 on both sides to get this down finally down to 4x minus 2y plus z equal to 6. And that would be the equation of our tangent plane. All right, part B, so that was part A. Part B wants us to find the normal line to the surface at this point, right? And so the way that you can do that is we already talked about that the gradient is always normal to the surface, right? That's just a property of the gradient. And so what we really need is a line which points in the direction of the gradient and passes through the point 2, 2, 2. So remember, we can parameterize this. So the equation of a line can be parameterized to be something like this, where you have x equal x naught plus some coefficient here, which is actually going to be f of x at the point 2, 2, 2 times t, y equal y naught plus f y at the point 2, 2, 2 t, z equals z naught plus f of z at the point 2, 2, 2 times t there. Well, you kind of, if you want to write this in terms of vectors then, right, we can now substitute in here everywhere a 2, as we're at the point 2, 2, 2, and then here we can substitute in the partials that we calculated when we did the gradient, the 16, the minus 8, and the 4. Or another way that you might write this is say, well, I can just write this parameterization like this guy. X naught, y naught, z naught, plus the gradient of f, right, times t here. And let's just write out what that would be for our problem. That's with the exact points and everything. It would be 2, 2, 2, plus, and then we said it was 16 minus 8, 4, all times a t. And if I want to simplify that out, I get 2 plus 16t, right? Just adding the vectors together, I get this type of thing going on with all of those components now a little bit prettier. And they would look exactly the same as up here, right? If I substituted in all of those points there, I would get 2 plus the 16t, 2 minus 8t, 2 plus 4t. So either way you want to write it, if you want to do that parameterization this way, or if you want to write them as vectors, that way both define the equation of that line, which is normal to the surface at the point 2, 2, 2. Okay? All right, hopefully that helps you with one of your problems. Let's look at the next problem that we're interested in solving here. So this one says we need to find the point in the plane 2x minus y plus 2z equal to 16, which is closest to the origin. So the first thing I would want to do here is let's just solve for one of the variables. We may as well solve for z. And then we'll go through a minimization process and we'll kind of show you the way to solve this. So first, let's solve for z in the equation of the plane. So if I do that, I get that z is equal to 16 plus y, let's see, what, minus 2x, but then I'm going to have to divide each term by 2. So that's going to be all over 2. Or maybe I rewrite it this way, equal to 8 minus x plus y over 2, something like that. Okay. All right, so that's a different way I can write the equation of the plane, now having solved for one of the variables. Really, I didn't do anything yet. But now is when we start to do something interesting here with the calculus. So what we need to do is we need to figure out what is the distance function from the origin to a point in space, right? And that is going to be defined by this guy, f of x, y, z equal to x squared plus y squared plus z squared. All right, and I really, if it was going to be the true distance function, I should take the square root of that, right? But so I'm going to, that will be too complicated. So we will minimize the square of the distance. From the origin. Right, so this is the square of the distance from the origin, right? If I put the square root around it, that would give me the true distance, but we're going to minimize the square of that distance. And so now it becomes useful having solved for the written equation in this form, because now I can say, well, I'm really going to minimize the function f of xy equal to x squared plus y squared plus z squared, where z squared, where z is equal to this guy right up here, right? Where that's where I substitute in z for those other two variables, right? So now I just have an equation in two variables, plus y over 2, square him. Now I need to find critical points, right? Compute the partials and set them to 0. So let's compute partials and then set them to 0. So that's going to be f of x. Let's just do this quickly here. Well, before I do that, let me just go back for one moment and let me move some of this down. Sorry, I just want this to be easy so you can compute the partials without thinking too hard, right? Let's write this as x squared. Let's just simplify this out in one step. So if you just do the algebra, you get this coming out of it. 2/4 y squared minus 16x plus 8y minus xy plus 64. Okay? Right. Okay. So nothing magical happened there. I just, in this line, squared all this out in collected terms, right? I didn't want to go through the horrible details that might have been, so I had done the calculation before, and now I'm just writing down what you would get there. But you can go ahead and verify it and make sure that you get the same thing. So the partial of f with respect to x then would be 4x, right, from this term, minus a 16 minus y. And I want to set him to 0. And then I have f, the partial with respect to y, would be 5/2 y, right? The 2 comes down and cancels with one of the 2's in the factorization of 4. So 5/2 y plus 8 minus x, set him to 0. So now what you do is solve this system of equations for x and y. So here you can rewrite these if you want as 4x minus y equals 16 and 5/2 y, or maybe I move him over here just so you can see, minus x plus 5/2 y equal to minus 8. So I'll just move things around so that x's line up and y's line up. And then you can use your favorite method to solve this. Substitution, right? Solve for y here, plug it in here, and then see what comes out. Or elimination, multiply this whole bottom guy by 4 and then add them together and solve for one of them. I think that you should know how to do this, but just in case, let's just do it really fast. It's not too hard. So I have 4x minus y equals 16. And then what I'm going to do is multiply the whole bottom equation here by a 4. And the reason you see I do this is because then things just cancel nicely. So I get minus 4x plus, now the 5/2 gets multiplied by 4, and what do I get out? I think it's just 10. Y equal to minus 32. Okay, now add them together, and I get that these guys cancel out, and I am left with what? 9y equal to, adding those together, what do you get? 16, negative 16? Alright, so then solving for this, that means that y is equal to minus 16 over 9. Okay, Now you can use that into maybe this top equation, right? So you have solved for one of them. Now you go plug him back into one of these equations. So I'm just going to plug it back into the top one. Now, for x minus y, I discovered was negative 16 over 9, so that will be plus 16 over 9 will be equal to 16. Subtracting things around, you find that x is equal to 32 over 9. Okay? Now I need to go back completely to the equation of the plane and solve for z. So now I go back to the equation of the plane and solve for z. So let's look at that. Z we found up here was what? Equal to, we wrote it right here, 8 minus x plus y over 2. So that was 8 minus x plus y over 2. Now we plug in what we know. We know that x is 32 over 9 and y is minus 16 over 9. Divide this whole thing by 2. I trust that you guys know how to do a little arithmetic here. If not, you can probably plug it in a calculator and work through how you would get it, but it's 32 over 9. So the point here that we needed to find, which was closest to the origin, is this x, y, z equal to 32 over 9 minus 16 over 9 and 32 over 9. Okay, let me just review it really fast in case you maybe got confused at any step. The first thing is we looked at this plane and we said, okay, let's solve for one of the variables in terms of the others. And then we needed to minimize the square of the distance from the origin to a point in 3 space, right? And the point in 3 space is a point in which the z is defined by the point that it is on the plane, right? So that's the part where we introduced the plane into this distance equation, is when we set z equal to this 8 minus x plus y over 2. Then we took partial derivatives of this guy and set them to 0 and solved the resulting system for x and y, right? We solved that system for x and y, and then from those x's and y's we can plug them back into the equation of the plane to solve for the corresponding z, right? And so then we got a point on the plane which we know is closest to the origin because it minimized the square of the distance function. So this is the key here, understanding that that is our distance function. And if it was at a different point, you would do instead something like x minus x naught squared plus y minus y naught squared, where this point now is the point that you're interested in getting the closest you want to, right? Say the point had been 1, 1, 1, I would just shove a 1, 1, 1 into those places. Okay? In our case it was 0, 0, 0, so that made the problem a little more simple, but not bad in any case. All right, so hopefully the strategy to solve this problem helps you with some of the problems on your homework. And that's the end of our video for the week.